Hello friends, today in this video we'll discuss regarding the laws of illumination. There are three laws of inverse square, Lamberts Cosine Law, and from this there is a cosine cube law. Laws are required or important to find out the size candela power of the source, illumination level on the surface, and from this we can decide the illumination level required for the various applications. So first we start with the inverse square law. So for this we'll consider the light source which emits the light equally in all the direction, in all the 360 degrees direction. So this light source is placed at the center of a hollow sphere. So this is a hollow sphere, and at the center of this hollow sphere this light source it is placed here, and the light emitted by this source, it falls uniformly on the inner surface of the sphere. Means if we consider the square millimeter area inside this surface, so all these millimeter square area receives the same amount of light inside this sphere. So initially we placed this sphere with the radius r1 or having the radius r1, which receives this same amount of light on each square millimeter. Now if we replace this sphere with the larger radius, that is r2, and with this larger radius r2, again the total amount of light is spread over the larger area. So this light is proportional to the square of this radius. It is proportional to the square of this radius. Again, for this radius r2, each square millimeter it receives the same amount of light. So this amount of light which falls upon any square millimeter of such a surface will therefore diminish or decrease as the radius increases, and it will be inversely proportional to the square of the distance. Means for R1, say there is a certain illumination, and as we increase the radius of this sphere, the light receives, it is decreases. Again further we increase the radius to R3. Means from this light source, if we move away, the light falling on this inner surface of this sphere, it decreases. So this inverse square law, it states that the illumination at a point on any surface is inversely proportional to the square of distance between the surface and a point source, provided that the distance is sufficiently large so that source can be considered as a point source. Now here we'll see this is a point source. So initially there is a radius r1, we increased this radius r2. So as from this point source we increase the radius or we increase the distance of this surface, so the light receives on this surface, it is inversely proportional to the distance between point source and the surface. Now for this we'll derive this law. So for that, so there is a light source, and to this light source we placed A1, A2 and A3, these three parallel surfaces, and these parallel surfaces, they form pyramid at the different distance. Okay, so with this line with this square surface, the pyramid it is formed. And the areas of these surfaces, they are proportional to the square of the distance. Now we consider the areas of these surfaces are A1, A2 and A3. The distances from the point source to these areas are say D1, D2 and D3. So D1, D2, D3 are the respective distances from the point source to A1, A2 and A3. So this point source S is having the luminous intensity I, and the intensity or light rays, they are normal to these planes. They are normal. Normal means perpendicular to the plane A1, A2 and A3. So for this pyramid, solid angle omega is subtended by these light rays, and luminous flux radiated per steradian is I. So from this we can find out the total luminous flux radiated by this point source S is equal to luminous intensity multiplied by solid angle. So in this omega solid angle, the light source having the luminous intensity I, so solid angle multiplied by luminous intensity, so we get the total luminous flux radiated by this point source. So illumination on the surface area A1. So this I omega lumens, they are radiated by this point source. So we find out the illumination level on the surface A1, A2 and A3. So first we find out the illumination on the surface A1. So which is equal to flux radiated by this point source divided by area of this surface. So flux upon area. So E1 is the illumination at surface A1, which is equal to I omega, total luminous flux radiated by the source, divided by A1, area of first surface. And it is lumens per unit area. It is lumens per unit area. Now we can find out the area A1 from the solid angle and the distance from the point source and area A1. So which is equal to omega d1 square. Omega d1 square. Okay. So we substitute this area A1 in the equation of E1 or illumination on the surface area A1, and we get E1 is equal to I omega upon omega d1 square. And here this omega it get cancelled, and I luminous intensity of a point source divided by d1 square, distance between point source and area A1. So this is the illumination level E1 on the surface A1, on the surface A1, I upon d1 square. So similarly, we can find out the illumination level on the surface area A2, which is having distance d2. So E2 is equal to I omega. So this flux radiated by the point source, it is a same, only area of this A2 plane it is changed. So solid angle multiplied by distance between point source and surface area A2, d2. So I upon d2 square, lumens per unit area. Similarly, the illumination level for surface area A3 is equal to E3 is equal to I upon D3 square. And if we take the ratios of E1 is to E2 is to E3, we get I upon D1 square is to I upon D2 square is to I upon D3 square. And from this we can conclude that the illumination E is an illumination level on the surfaces. So D1, D2, D3 are the distances from this point source to this area A1, A2, A3. So this I, intensity of the point source S, it is a constant. And from this we can conclude that the illumination level on the surface, it is inversely proportional to distance square, or illumination is proportional to 1 upon distance square. So this is the law of inverse square. So illumination at this surface A3 is 1 upon D3 square. At A2, 1 upon D2 square. At A1, 1 upon D1 square. So the illumination at the surfaces, it is inversely proportional to distance square. It is inversely proportional to distance square. Now we see the Lamberts Cosine Law. So the illuminated surfaces, they are not perpendicular to the direction of the light. So in our house, or in our, say, we consider the room, bulb or light source, it is placed on one wall, and from this light source, so light is emitted or radiated in all the directions. So they are not perpendicular. So there are vertical walls, remaining 3 walls, then there is a floor area. So it is not normal to the direction of this light rays. The illumination at the surface is maximum if the light falls normally on the surface. So we consider the case of say street light, and if we stand exactly below the street light, so we get the maximum illumination level, and if we move away, then the illumination level, it goes on decreasing. So the surface is inclined to the incident light, the illumination level, it is less or it decreases. So this Lamberts Cosine Law states that the illumination at any point on a surface is proportional to the cosine of the angle between the normal at that point and the direction of the luminous flux, or the incident luminous flux on that surface. So this is the Lamberts Cosine Law. So illumination at any point on the surface is a proportional to the cosine of the angle between the normal, means perpendicular to the incident rays or the direction of luminous flux at that point. So again we see the mathematical derivation. So let S be the point light source. So this light beam, black color light beam, black color line is a light beam from this point source S with an intensity I, which incident on this normal, on this plane CD. So this violet line, which is a perpendicular to this plane CD, and the angle between this normal and this incident ray, it is theta. So D is a distance of the source from the source and this surface CD. Okay, so this D is a distance between light source S and the point O on this surface CD. So phi is a total luminous flux in the lumens received on this surface. Okay, so this CD surface, it receives the total luminous flux phi. So here the same thing it is shown here. So this is a incident rays, light rays, and this plane is a perpendicular to this light rays. It is a perpendicular to the light rays. So this AB plane is a perpendicular to this incident rays, and this is a CD plane. This is a plane CD, so which is inclined at point O by an angle theta, with this plane AB. So this, how this angle theta and this angle theta, it is the same. It is explained in this diagram. So these are the light rays. They are perpendicular to this plane AB at this point, and at this point we incline this plane. To the second position CD. Okay. So we can observe this angle theta between this incident rays, which are perpendicular to this plane AB, and after this inclination at this position 2, this is a plane CD. So this angle is theta. Similarly, between these two plane AB and CD, this angle is theta. So from this diagram, you clear this idea. Once again, we can see here. So this is the normal to this plane AB. Now we inclined this plane to the second position CD, and these are the angle theta between the plane AB and CD. So here this is a normal to this plane CD. This is a incident rays, so this angle theta, and the same angle theta is there between plane AB and CD. So omega is a solid angle. Then illumination on both plane is same. So with this solid angle omega, it is the same for both plane AB and CD. So the illumination on plane AB and CD, it is same. So we find out the illumination is equal to luminous flux received upon the area of the surface. So from this figure, we can find out the relation between plane AB and plane CD, which is having angle theta. So there is a cosine relation. Cos theta is equal to plane AB upon plane CD. So cos theta means adjacent side, means plane AB, upon the diagonal, means plane CD. Okay, so cos theta is equal to plane AB upon plane CD. So area, we can find out this relation, cosine relation, in terms of area of this plane AB and plane CD. So area of this plane CD is equal to area of plane AB upon cos of theta. So solid angle omega, which is equal to area upon radius square or the distance square. Area of the plane, area of the surface, and the radius means the distance between light source and the surface. So this is the solid angle. So here we substitute the area of plane AB, A suffix AB and A suffix CD. So these are the area of plane AB, area of plane CD, and the distance at point O is d square. So distance d square. So solid angle we can write in terms of area and distance, area of AB upon d square, which is equal to area of CD plane upon d square. So both the plane AB and CD, they are having the same illumination level. So E is equal to luminous flux received on this plane upon area. Okay, so it is a luminous flux, intensity of light source, and the solid angle with this surface omega upon the area of this surface. So in this equation of this illumination, we substitute the area AB, area of AB plane, area of CD plane, this intensity and solid angle, it is the same for both plane. So I omega upon area of AB plane, I omega divided by area of plane CD. But we find out the area of plane CD, which is equal to area of plane AB divided by cos of theta. So we substitute here the area of this plane CD, and the solid angle omega is equal to area of plane AB upon d square. So here we replace this solid angle with this equation, and we replace this area of CD plane with this equation. So here I multiply by solid angle is equal to area of plane AB upon d square, total divided by, now we replace this ACD, is equal to area of plane AB upon cos of theta. So here this area of plane AB, it is get cancelled, and we get the final illumination E is equal to I upon d square multiplied by cos of theta. So in this equation, the intensity of the light source I and the distance from this light source to point O, it is a constant. It is constant. And this illumination E on the surface CD, illumination on the surface CD is proportional to the cos of theta. It is a proportional to the cos of theta. So I upon d square, this term, it is a constant. So illumination at plane CD, illumination at plane CD is proportional to the cosine of angle between normal plane, normal means which is normal to this incident light, and this inclined plane at an angle theta with this normal plane. So this is the Lamberts cosine law. Now we'll see the cosine cube law. So for this cosine cube law, so we consider the surface CD. Ny is a normal to this plane CD. X, Y, this is a line of flux or the incident light rays from this point source S. X, Z is a height of light source, okay, or the light source is mounted at the height h from this level or from this CD plane at a height h. The angle NYX, so this is a theta, and the angle ZXY, it is a theta. So with this normal or perpendicular distance from this light source to this surface, or the normal to this plane CD, and the light rays angle, it is a theta. So according to the Lamberts cosine law, illumination E is equal to I, intensity of light source, upon distance square multiplied by cosine of this angle theta. So this is the illumination on the surface CD at point Y. Okay, so which is equal to I upon d square cos of theta. So from this diagram, there is a right angle triangle X, Y, Z, and from this right angle triangle XYZ, so we can write down cos of theta is equal to XZ adjacent side. It is nothing but the height of the light source from this ground upon the diagonal XY, which is nothing but the distance D between the point source and this surface CD. So cos theta is equal to height upon the distance. So D is equal to height upon cos of theta. So we take the reciprocal of this D. 1 upon D is equal to cos theta upon H. Now we substitute this 1 upon D in the Lamberts Cosine Law. So illumination E is equal to I, and 1 upon D square means cos square upon H square multiplied by cos of theta. So this is the Lamberts Cosine Law. I multiplied by 1 upon D square multiplied by cos of theta, and 1 upon D square is substituted by this cos square theta upon H square. So this term 1 upon D square, it is replaced by this equation, and the illumination E on this surface CD, which is equal to I, intensity of light source, upon mounting height square of the light source multiplied by cos cube theta, and cos square theta multiplied by cos theta, which is equal to cos cube theta. So this cosine cube law is the illumination of a surface at any point is a proportional to the cube of cosine of angle between the line of flux from this point source or from this light source on this surface, and the normal to the surface at that point, and the normal to this plane means perpendicular at that point on this plane CD. So this is the cosine cube law. Thank you for patience listening. Thank you.